Welcome to this lecture on flip-flop operation. This is part of our module 3, which is sequential circuits for near threshold voltage operation. First we will discuss what is the importance of flip-flops and sequential circuit elements, and then we will discuss the operation of conventional flip-flop. We will briefly review that and the timing requirements. So, setup time, hold time, clock to Q delay, etc. So, flip flops are synchronous as well as in asynchronous circuit design methods. Flip flops are the one of the fundamental circuit elements which help synchronize the signal flow, and they become very critical and their operation becomes very challenging in near threshold voltage domain. That is why we are specially discussing flip flops in a detailed manner. So, in sequential or pipelined architecture, what you find is that you have a capture flip flop, a launch flip flop and a capture flip flop. So, data is ready here at the clock edge, the data is passed through the D latch through the D flip flop, it is passed to the output Q, and then it goes through some combinational logic processing, and that processed data is now available at the capture flip flops input D before the next clock cycle. So, the timing diagram, if you want to see, could be like this. So, suppose this is a positive edge triggered flip flop. These are positive edge triggered flip flops. So, suppose the data D changes here. So, you would observe that Q1 would change here and D into with a delay, it could be inverted or non-inverted with a delay, D in T2 would be available somewhere here and Q2 would change here at this edge. So, this is the operation that you would see. How does the static flip flop work? So, this is a master slave flip flop and this is the most basic flip flop, and if one understands this flip flop, this is mostly used and its variants you will see in most of the other flip flops. So, therefore, it is important to understand the operation of static. So, how does this work? So, this is the master stage and this is the slave stage. The input D in, suppose the clock is 1 initially, suppose we are discussing the clock this way. So, let us call this T naught, T1, T2, T3 at T naught. So, now between T naught and T1, this is on T naught and T1, this transmission gate is on. So, therefore, input between T naught and T1 is available in an inverted form at Q2 and therefore, with some delay at Q3. That delay should be such that the input is available before T1 or Q3 is available before T1 in its full value, and now Q3 is available before T1. When after between T1 and T2, this transmission gate M12, M13 is transparent and therefore, Q3 would pass on in an inverted manner to Q5, whereas transmission gate M2 and M3 is off. Therefore, whatever be the change in D in between T1 and T2, that change would not pass on to Q2 or Q1 and therefore, Q3. What would happen? There would be this feedback path M7, M8 is also transparent between T1 and T2. So, therefore, Q3 would restore Q2 if there is some change in Q2 because of some noise or whatever be the reason. So, likewise is the operation of the slave stage. So, once the clock turns low, that is at T1, after a while the delay, after the delay from Q3, because now this transmission gate is on. So, after the delay roughly from Q4 to Q or Q3 to Q, your data is available. So, this is a negative edge triggered master slave flip flop. Yeah. This transmission feedback transmission gate is again available between T2 and T3 or between T0 and T1 like this. Okay. So, what is the clock to Q delay? Clock to Q delay is approximately the delay from Q3 to output Q when the clock turns low, that is clock bar turns. Let us look at this operation through a simulation result in 65 nanometer commercial PDK, in a 65 nanometer, using a 65 nanometer commercial PDK. As you can see, this is the clock is turning low and clock bar is turning high. So, before the clock turns low, the input passes on to Q1 and Q2. This is Q1 with some delay, Q2 is also available, and then this is Q3. So, Q3, the inverted version of Q2, is also available before this clock switching takes place. After the clock switching, this transmission gate is on and therefore, Q5 is available, right. So, Q5 would be available after the clock turns low. So, Q5 would be an inverted version of Q4. So, this is Q4 and it would be an inverted version of Q4, and then after a while, after some delay, an inverted version out would also be available. Okay. So, but this happens after the clock turns low, as we have discussed previously. So, this is the master slave flip flop operation, and clock to Q delay, this is clock to Q delay. The Q has changed after a while passes from the switching off clock. Where does this fail? If we plot, suppose the clock is 0, so this transmission gate is off. So, Q2 and Q3 would be restoring each other. If Q3 is VDD, Q2 would be 0 through this, because clock is 0, clock bar is 1. So, this transmission gate is transparent. So, this is the static transfer characteristic of M4, M5, and this is the static transfer characteristic of M6, M9 plus the transmission gate M7, M8. So, now this has 3 possible states. This state is that Q3, this state is when Q3 is at VDD and Q2 is 0, and this is when Q2 is VDD and Q3 is 0. So, this is logical 1 and logic 0, because these are near threshold voltage circuits. They would, if they are near threshold voltage circuits, they would really not be VDD and 0, they would be the lowest value would be slightly higher than 0 and highest value would be slightly lower than VDD. But there is also this metastable point, and what is its value? We will discuss further. So, this metastable point becomes important if you violate setup time or hold time of the flip flop. So, what are the setup time and hold time? The input data, as you know, should be available sufficiently before the clock. So, for this negative edge triggered clock, sufficiently before the clock turns 0, and the input data D in should not change till a while after the clock turns 0. So, that time is hold time. So, these are setup and hold times, and these should not be violated. If these are violated, it may result in the metastable condition that we had discussed just now. So, how does that happen? So, here we are looking at a scenario. These are again simulation results in using the 65 nanometer commercial PDK. So, this is the data. So, these are now for near threshold voltages. It is not exactly near threshold, but it is a low voltage operation that you are seeing. So, here the value of D in is changing quite close to the clock, as you can see, it is changing quite close to the clock. So, due to that, Q2 is not getting sufficiently charged before the clock turns 0. Q2 is not getting sufficiently charged, but nevertheless it is Q2 is getting charged to a value above the inversion threshold of M4, M5. So, the delay of inverter M4, M5 is increasing fully to VDD. So, that is causing the delay of M4, M5 to increase, and that increase in delay of M4, M5 is again causing and the value of Q5 not to be sufficiently charged to 0 when clock turns high. So, Q5 is also charging slowly, because Q3 is charging slowly, Q5 is discharging slowly. That increases the delay of Q, output Q. So, that is why we find that when D is coming very close to the clock edge, when D is coming very close to the clock edge, output Q is moving away. So, there is the delay between the clock edge and output Q is increasing. In this case, it has increased extremely. So, a traditional industrial definition of setup time is that clock to queue delay, when it increases by 10% or 5%, every industry chooses a different value. Suppose we choose 10%. So, when the clock to queue delay increases by 10% from its original value, when the difference offset between D in and clock is insufficient, we call it original value. So, when clock to queue delay increases by 10% from its original value, we call it setup time. So, setup time violation means you have reduced the D in to clock offset to such a value that the clock to queue delay has increased by more than 10%. There is another definition of setup time, that the D in to clock offset has been reduced to such a value that the value of Q2 and Q3 remains at metastable point that we had discussed. So, this is a more fundamental definition, but the industrial definition is of 10% or 5% increase in clock to queue delay. Likewise, hold time. So, in this simulation result, you would see that data is changing after the clock edge, but what is that resulting in? So, after the clock edge means the clock does not have a step nature, it has a finite transition time, non-zero transition time. So, when the data changes after the clock edge, so if we take the clock edge at 50% clock value, some transmission of the change in data would occur at Q2 and that would result in a change in Q3, and here again and the slave stage, the clock again has a non-zero transition time. So, that would result in a change in Q5 and subsequently a change in value out Q, which is unwarranted. This is not a change that is wanted. So, the clock now, so after the clock the D in is changing and that is changing Q bar, but it is getting restored. But if the value of Q bar touches the metastable point, if it changes so much, then there is a large time after which it is restored and it can be restored randomly to either VDD or 0. So, this is a hold time violation. So, in this lecture we have discussed the basic operation of master slave flip flop and its clock to queue delay, its setup time and hold time violation. What are the consequences of these violations? Thank you.